least my mindset changes when I come here. I was reading this message Casper wrote, and it says here. Then I imagined that this is happening actually here, and it was very troubling to me. But so I will. Some of you have heard this talk at some version of it. I hope you will still find it interesting. So it's about two ideas. One is round elimination, which is a very simple way to prove lower bounds, conceptual way. And another is triangular discrimination, which is a measure of distance, which is useful for performing round elimination. So the two parts of the talk are these two parts. And so we will start with round elimination, then we will discuss this distance, and then the only thing that we actually prove is some example. I will show some example that is meaningful, I think. So the round elimination is this is a very simplistic model, or maybe to actually make it into a model you need to say more things. But so there is some computational process, and it operates in rounds. And in every round, it says something. So in round I, it says mi. Mi depends on the input x and what happened before. And the last message, mr, or the last thing that happened, should tell you something about x, the input x. And the type of thing we would like to show is that r should be large, that to achieve its goal, the computation must operate in many rounds. This is the type of problem we want to, type of question we want to answer. And okay, so this is okay.
Usually there is a trade-off between how much you record and how many rounds.
Yeah, so to make this specific, you need to say more things. Even, you need to put some restrictions maybe on the model. So the way round elimination suggests to operate is something like this. We want to find something that is hard for R rounds. I call it XR is the input for the R round problem, and FR is the type of thing we want to compute. And the way we do this is we construct them in some way so that if we have this and we have some solution for this problem in R rounds, then this gives us a solution for some other problem that we already constructed for R minus 1 rounds. So this is the logical structure of the proof. We want to find something that is hard for R rounds. We construct it in a specific way that allows us to, from the solution for something that is for XR and FR, we get a solution for XR minus 1 and FR minus 1. This we need to do for the specific model we are interested in. And then after we do this for R times, we reach X0 and F0, which are supposedly solved without any rounds of anything. And this should be impossible, because they are somehow non-trivial for the model we are interested in. So this is the round elimination idea. And typically what happens in this type of procedure is that there is some error in the computation, and it keeps growing throughout the application of this idea. So in the beginning it is 1/10, then it becomes 1/3, and then it becomes something else.
Less than one.
So hopefully the whole argument we find is that the error here is still somehow meaningful. The specific model in which this idea was first suggested, I think, is communication complexity, the two-party setting. So here is what the four people I listed before suggested to do. So in this model, there are two players, Alice and Bob. Alice gets an input X, Bob gets an input Y. And then they talk. Alice says something, a message that depends on X. Then Bob says something, a message that depends on Y and on M1, and so forth, until they communicate the last message. And so this is the model, and I guess you know it. So the way the round elimination should go like this, at level 0, we find something that is hard. F, so F is some hard function for when there is no communication. This is pretty easy to find such a function. Then for one-round protocols, what we should do, we should duplicate Alice's input some large number of times, n times, and give all of these n things to Alice. Bob will get some part of X. Let's say so we choose some J. This is upon our, so we choose some J, give Bob everything before J, and some Y. And the goal of Alice and Bob in the level 1 thing is to compute f of xj and y. So this should be harder than this, in the sense that Alice needs to say something about xj, but she does not know what j is. So her communication is sort of split evenly between these things, and this, therefore, should be harder. This is the intuition, and you can make this formal in some sense.
In level 0, you mentioned that there is no communication, so now there is communication in level 1.
In level 1, there is one round of communication.
And it sends a message to Bob.
Yes. And then you can make this concrete in many models, not just communication complexity, but I will not mention this, not talk about this. Okay, so this is the round elimination idea, and you can prove lower bounds on communication complexity using this. And I want to suggest some other perspective on the same thing. Don't eliminate rounds. This will lead to losses in the argument. So here is a different perspective on the same proof. Instead of eliminating rounds, do something slightly different. Show that when you communicated for I rounds, then some messages M were sent in these I rounds. Some data was collected in these I rounds. And look on the distribution of the variable that comes from the R minus I construction without any knowledge of anything. This is this distribution. And compare it to the distribution on this thing when these messages were sent in these I rounds. So we compare a distribution where nothing happened to a distribution where the whole thing operated for I rounds. And try to argue that in every step, the distance between what we learned and so this captures somehow what we learned in these I rounds, what we learned about this part of the input. So try to argue that in every single round, this does not increase by more than epsilon for some epsilon. Okay, so here there is no elimination of nothing. We just look on the protocol and try to say the distribution of this, or the distribution of some part of the input is unaffected by the protocol. It's basically the same. So this is very close to this.
These are the last R minus I rounds. X to the R minus I is the last R minus I rounds.
This is some distribution that is hard, or that you got. So the distribution for R rounds is constructed in some gradual manner, and this is the distribution for the rest of the thing. Is it okay? It's confusing.
Should I think of it as the last round? Like I did some rounds?
Yeah, we communicated the first I rounds. There are R minus I rounds left, the last R, and this should be, this is the input to the last thing. Yes. Okay, so the reason I think this is a better system than eliminating rounds is that here we can write whatever distance we want. When we eliminate rounds, we basically must use statistical distance. This is part of the mechanism, the rationale. I'm not sure how to say it differently. But here we can write whatever we want, and there are many distances, and some of them are better than statistical distance. So this is the next thing I want to talk about is what type of distances we can use, and maybe one specific distance, which is called triangular discrimination. So this is it about round elimination. Not a lot of details.
So one thing we're not counting is what has the first I rounds of messages told us about the answer. Is that somehow encoded in this distance already? Or is that something that we have to work into the reduction or something else?
So eventually, it should be, if all of this thing, actually we can prove such a lemma, then we will have the distribution on XR, on X0, and the distribution of X0 condition on the whole protocol. If this number is small, then it means that X0 condition on the whole messages is distributed exactly as if nothing has happened. So this shows that the protocol does not achieve its goal. But it's a sort of the goal is actually almost irrelevant here. You just say the protocol did nothing. It said nothing about this part of the input. It's okay.
Maybe it's important that the rest of the input is not the answer. This is the answer.
Yeah, we construct the thing so that X0 is where the answer we are interested in is. Yeah. So this is round elimination. And now I want to talk about distances. So there are many ways to measure distances. And maybe a very big family of distances are called divergences. So these are the people related to this definition. So it's all so this is a distance. It's not a metric, but it's a sort of a divergence between two distributions. There is some distribution P and some distribution Q. And we want to define some number that depends on P and Q that is somehow related to their distance. So here is one way to do it. We choose any function, any convex function f we want. And we insist that at the point one, the one variable convex, nothing abstract. We insist that at the point 1 it evaluates to 0. Then we get this quantity.
Shouldn't it be T of omega in the coefficient?
No. So, okay. The next slide maybe help to will help you to understand. So, okay, this is some formula. Not so maybe interesting or not. It's hard to tell. Right? But basically, all the notions I know of are of this form, and they come with this definition comes with some nice properties. So maybe first some examples. So here there is a list of a graph of 3 functions. There is the function 1 minus x with absolute value. There is the function x log x. And there is this function, x minus 1 squared over x plus 1. This is this function. You can draw many other functions, right? It's very easy. So this function, the first one is L1 distance. This function. The x log x function is KL divergence, which is information theory. So maybe it helps to see.
So it's not log, it's just x log x.
Yeah, it's not log. Log is actually not convex, but x log x is. So it's x log x. This is the right way to write it, which is a strange, right? It's like writing. So we write the KL divergence as some. It should be.
P of x, P of omega log.
So it should be. This is how we typically write this, right? But the way it is written here is like this. It is the same thing if you treat division by 0 correctly. But somehow in this version, it is much easier to understand it. So I will show some. So it's a strange. So, and basically everything you can put into this and you will find some f, every metric we use. So the properties this definition comes with are 3 simple properties. One, it's a non-negative number. This is pretty good for a distance. Second, because f is convex, this function is convex. In the abstractly, this is just some point in some space, and it's convex in this input. And the last property that holds also by convexity is what is called the data processing property. If there are 2 distributions over the same space, x and y, and then we apply g, some function on this space, so we get g of x and g of y, the distance of this is smaller than the distance of this. We process the data, the distance can only shrink. So for mutual information, this is called the data processing. Maybe it's more well known, but this is always true in this generality. Okay. So this makes it a nice family of distribution, and there are more things that people know how to, like more properties about this. We are okay? Yes. Now, for when we actually try to prove lower bounds, it's very important to switch between different distances at the right time. So one way to do this, very, very useful, is Pinsker inequality, which relates L1 distance to KL divergence. This is a very useful tool, inequality. Now we are in. So delta, I introduced it here. It's the thing you get when you use this function.
Where does the name come from?
So.
It comes from delta. I think triangle stands for delta.
Yeah. Yes. So there is some other thing, some other object which has the word triangular in it, and this notion captures the unit distance between these triangular things. So there is some reason. So now I want to tell you about this triangular discrimination. So it is almost L1 in the sense that it is smaller than L1 and not much larger than L1, as in Pinsker. And here I wrote delta again in a more clear way. It's like L2, but we divide by the sum. Not L2, L2 squared. And the last thing, which is most important to us, is that when you try to do Pinsker with this, there is no square root. So this is the most important property for us. So there is an analog of Pinsker, but there is no square root. All of this, Pinsker and this is like a two-variate problem. There are in calculus with two variables. This is what it reduces to.
But if we want to relate to L1, we go back to the square root laws, right?
Yeah, the minute we go to L1, we lost. Yeah. So the point I want to make is that we should keep this throughout. And maybe another property. I'm not sure how much time I have.
Some 4 or 5 minutes.
4 or 5. So I will show you. I will finish. I will not say everything I planned. But, so another important property of an object is to understand its operational meaning. What can we do with this? So specifically in this context, we have we are interested in statistics. So what are the type of tests we are allowed to use to test our statistical hypothesis? So L1 corresponds to tests whose L infinity is bounded by 1. So when we measure distance in L1, it corresponds to the maximum difference between the answer for a test with P and an answer for a test with Q, where this test is bounded by 1, pointwise. So this is L1. This delta, this triangular discrimination, is also the maximum distance between the answer of two tests. There is a square here. But the tests are no longer bounded pointwise, but only in variance. Just the sort of the variance of the test is bounded. So this is a much more loose condition. This is a pointwise thing. This is an average thing. So delta can be applied more generally. With more tests, it is meaningful. Okay, so this is a triangular discrimination. And now I just want to show you the example. So it was used in several works, unexpectedly, I would say, in group theory. It's very so here is the example that drives all of these information theory proofs. There is some random variable on the cube with very, very high entropy. And the way we write it in this language, the distance of the distribution of X from uniform is K, the KL divergence. So, okay. Then what KL divergence allows us to do, which is amazing, is to do subadditivity. What does it mean? It means that if we choose a random coordinate and look on the ith coordinate of X, it will be close to a uniform bit, and the distance is divided by n. This is the property of divergence that makes it most useful for us. And then if you use p-square, we can deduce that a random coordinate is almost uniform with this loss. When we go to L1, we lost this factor. Now I want to suggest, or this type of question is useful to understand when we actually try to make these arguments. Instead of choosing a completely random coordinate, we choose some coordinate j, which is, it's not completely uniform, but it is close to uniform in divergence. So we perturb it slightly, the distribution. Now epsilon is small. It's not k. It's actually small.
What's the difference between PL and J? I'm confused.
This is the distribution of I, which is uniform on the numbers between 1 and n. And this is some distribution on the numbers 1 to n that is close to it. Now we can ask ourselves, now we choose some other random index with some other distribution. Is it that this is close to uniform? So the first answer is yes, but it is a red yes. It's not so good. If we use p-square, then we get that the distance is this distance, square root, plus the previous thing. So this is a p-square, and so this is simple. Now the point is that when we do delta, there are no square roots. You just get this. So you can perform the whole argument and never write a square root in the process, which is a pretty good thing. So if you do this, you can actually improve parameters in many cases. So this is the example, and then there is a proof of this example. It's not so interesting. And this is the summary. So the way, at least I think about it, we want to analyze some expectation, and the distribution is too complicated for us. We have no way to do this. P. What do? We replace P by some other distribution Q, which is very simple for some reason, but it is close to P in terms of this delta. If we are able to do this, and the variances of G are controlled, then we are good. We achieved our goal. So this is now I'm quick because we don't have much time. I guess I'm over time anyhow.
Clock's fast.
What?
Clock's fast.
Yeah, so yeah, I guess I'm very slow. So just a summary, there is this idea of analyzing, proving lower bounds on the round complexity. And one way to do it is using round elimination. It's a pretty good way. Then there is a vast collection of distances that we can use, and maybe we should find some other out there that are useful. And specifically, this measure helps to remove the square root, so it makes all of the arguments quantitatively better. This is it.
So is it only quantitatively better, or is it also somehow simpler, the proofs at the end, or are they the same complexity?
I would say they are simpler, but in the sense that so they are simpler just in the sense that once you introduce this type of argument, there is no conditioning on just analyze some expectation and just need to. So in this sense, it is simpler, but you can do the same with L1 as well. And then you will just write square roots sometimes. So it doesn't, in this sense, it doesn't simplify the proof.
So there are a lot of different F divergences that can remove square roots in various situations.
Yes.
Do you have a sense for when this one is the right one to use?
So this was at least my intention when I said this high-level thing. So I will just, or maybe it's, maybe I will write instead of, yeah. We just want to try to understand. We want to understand the average of, I don't remember. This is something we want to understand, the average of G, the expectation of G. Now, this is too hard for us. Then we write it. Just write this. And now, when we write this, automatically delta comes into the picture. Sort of, delta allows to treat such an expression. So delta will take care of this, and then we just need to. And this type of operation happens. It's a natural thing to do sometimes. So, for example. When, I'm not sure it will be clear. When there is some underlying martingale, then Q can be the next step in the martingale. And then you just, this is a natural thing to do. So Q is defined somehow from P by an extra step or one less step. And then this is related to some property of the group or some other. So this is you just analytically replace P by Q in this very simple way. The motivation for this is different. I don't have one answer. But once we write this, delta is here. It comes automatically. We do one Cauchy-Schwarz, and you see delta. I hope it was clear.
I'd like to thank Amir again.